Okay, we made it. Happy Friday, week 3. We're fast approaching the, I don't know, first quarter mark of the semester. There is no, it's not next week. So 2 weeks from today, if I'm remembering my schedule and my syllabus right, which is 90% sure, 2 weeks from today is exam 1. Normally in this class, that would be just like in Analyte 1 and 2, a 2-hour out of class evening exam where we'd skip the next class after that. Given all of this stuff, I've decided instead of 2 midterms and a final exam to do just 4 straight exams in class. So they'll be shorter, designed to be finished in 50 minutes. The challenge will be, I'm pretty sure there will be people who aren't comfortable coming and taking it in this room. So I assume everybody who was here today in class and in person, that's not an issue for, but I'm still playing volley with a couple of ideas in my own head about how to handle the people who aren't going to be here. My 2 ideas right now are, and I guess this is more for the people who are joining by Zoom, so I'm going to talk straight to you. One, an oral exam covering similar kinds of questions, one-on-one, face-to-face, by Zoom at a different time. 2, a similar written exam with different problems, which I will Zoom with you and proctor at a different time, perhaps other than the time that we're taking it here in class. So I'll send out an email, and if you are not going to be able to be here for whatever reason, next 2 Fridays from now, we can decide exactly how we're going to handle that, just so you know that's coming up. I believe not next Wednesday, but the Wednesday after that, like the Wednesday right before our exam on Friday, is the rejuvenation day number 1. This is totally new. Instead of a fall break where we get a Monday and a Tuesday off in the middle of October, they're giving us 1 Wednesday off at the beginning of October. They're giving us 1 Tuesday off at the end of October or early November, and they're giving us Thanksgiving break off also in the normal time. So, right. Just so you're aware that that's some weirdness, not next week, but all happening the week after that. I'm opening up attendance now for people who are here because I forgot to do earlier. The number is 6074. If you're not here, please don't do it because the whole point of this is to know who's here. Okay, great. I'll leave this up for a second. All right, where were we? We had, there's a new kappa up. You have, I think, already enough to do a lot of it, and we'll get through most of the rest of the stuff you need to do it today. So have fun with that. So we are thinking about the double slit experiment. And we're thinking about, so we drew this on the board at the end of class last time. Here are 2 slits, right? And we have a plane wave coming towards these 2 slits in this direction. I asked, and someone answered correctly, what would happen to the light after it passes through the slits, or any wave. This is true of ocean wave, water waves, this is true of sound waves, this is true of any waves you could think of. If you have a barrier where you have a plane wave coming in and you have a barrier where you're only letting a small amount of that wave come through, you get a spherical wave coming out on the other side. And if you have 2 slits, you get 2 spherical waves, 1 where each of those slits is. So you get a situation that comes like that as they spread out circularly from the exit point of the slit. Why is that? Why wouldn't it just continue linearly? Oh, okay. No, if we were to close one of those slits, it would happen for the single slit as well. It would spread out. So the question is, would it happen if there were only 1 slit? The answer is No, the question was it only happen if it's two slits? The answer is no. Any number of slits. A single slit, it will spread out circularly from the one slit. Two slits, three slits, four slits, doesn't matter. Each slit, the wave will propagate circularly from that one point. I don't know. I wasn't there in semester one. But this is certainly, so the question is this how to prove that light is a wave and a particle? You don't, in fact, this is going to prove that light is a wave. There is nothing, you don't need particle theory to get a result that looks like this. In fact, all you need is a wave theory, because things that are waves and are not particles behave exactly like this, like water waves and sound waves and things like that. Okay, good. Good question. So why is it that if you block out all of the regions of a wave except for a single point, that point then radiates away spherically? You can think about this as emanating from something called Huygens principle. So here's a little side on Huygens principle. Actually, before I get to that, I managed to successfully install the right software that I needed to run these Java applications on Wednesday. So let's actually pull up, because this is kind of cool. Let's pull up some of these Java applications. Yes. Oh, I don't have one open. Classes. So we'll come back to Huygens principle in a second, but this now works. Where is it? Did I not drop it into the right? I didn't. I copied them into the wrong folder. Okay, now they're in the right folder, and now I can find them. And where'd they go? Oh, I didn't. All right, I'm not going to bother to put them in the right place right this second. Anyway, this should just work. Fingers crossed. It worked a second ago when I tried it. Woo! Okay, here we go. This is what the Java animation looks like. A Java applet looks like. You've got, again, you can download this from the PHET site. I can turn on a laser, and you can see for air on this side and water on this side, what those angles look like. Since water has a much higher index of refraction than air, you see that this angle on this side is much bigger than this angle on this side. We can move this around and see how this changes with incident angle, all the way from 0 degrees to 90 degrees. And you can see some of this bouncing off in this direction over here. Okay, so this is all fairly straightforward. This is straight up Snell's law. The interesting thing came when we changed from a high index of refraction to a low index of refraction. And we found that, again, now since we've reversed these, this angle, the exit angle, is much larger than the input angle. And that makes it so that there's a point at which the exit angle becomes 90 degrees and you get total internal reflection. That was what we were, this must be the critical angle, because if you make the incident angle any bigger than this, you've got total internal reflection. And anything on this side of it, you're total internal reflecting. We even calculated what that number was for air to glass. And if you remember, it was 42 degrees. We can see if this FET animation is doing a good job by putting a protractor down here, and lo and behold, we get a little bit more than 40 degrees. So it seems to have worked in the way that it should work. We could even put some prisms in here. This is almost exactly the same shape as the little bauble I had in my hand that I was doing demos at the beginning of class yesterday. And you can see how there's two angles now, two reflection angles now to worry about. One when it enters the glass and one when it leaves the glass. And both of them are important to deciding where the spot's actually going to go. But you can see as we move, actually I wasn't moving this, I was moving the prism back and forth, that does in fact change the spot, and you can see why and how the light path actually works. The other thing I wanted to show you was, reset this, when you see the wave part of this and turn on the, so one was just the ray view, and this is the wave view. You even get a decent glimpse of why refraction happens, how it is that changing the wave speed changes the direction of propagation. So I don't know if you can see this. There's lots of good things that are happening in this animation that you can see. First of all, you can see the wave speed. Let's make it a little bit faster, maybe be more obvious, is going definitely faster here than here. These peaks are moving at a faster rate than they are over here. These lines are supposed to represent the peaks of the waves as they propagate through, obviously slowed way down. You can see that it's traveling faster in air than it is in water. Let's make it glass so you can even see it better. You can see how much they slow down. And you can also kind of see why the angle matters. This is very much analogous to if you've ever been in a marching band and you're all marching in lockstep with one another. If the speed of that band were to change, obviously it would slow down. But if it were to start, if you were to encounter a situation, let's say, where you had some river and that river was slowing people down, and the people on the left encountered that river before the people on the right, you would exactly what is happening here. The lines would change in direction. If the lines are all pointing in this direction and this side goes slower first rather than the right side, then all of those lines are going to be tilted. Now, if your marching band is not quite analogous, because the marching band can keep going straight with a tilted line, light can't keep going straight with a tilted line. The very fact of tilting that line also tilts the direction of propagation. But that's basically what's happening. You can also see how the wavelength changes. Out here, the wavelength is pretty long, and as the wave speed slows down, the wavelengths get closer together. It's harder to time the frequency, but if you were to time the frequency of how many waves are going by in a given amount of time here, it would be exactly the same as the number of waves that are going by in a given time here. This is a very good picture, a diagram to show exactly what's happening in a light wave as it enters and exits a medium. So feel free to download this and play with it if you like. Okay, good. Great. Back to attendance. I'm going to close. You can go away. Back to Huygens principle. We want to understand why it is that these things come out in a spherical pattern after encountering a slit. So there's two parts of Huygens principle. First part is all points on a wave serve as point sources of secondary wavelets. Write that down. All points on a wave serve as sources of secondary wavelets. Those secondary wavelets do propagate spherically from every single point on the wave as it propagates. Item 2 is, after time t, the new position of the wave front will be a surface tangent to the secondary wavelets. Okay, that's a lot of words. What are we talking about? Let's think about a plane wave. So a plane wave, the wave front, you can think of as just like the wave front of an incoming ocean wave. It is the location of points where a peak in that wave happens a particular wave happens to be. It is the lines that we were seeing on the wave animation in the FET thing. That's a wave front. So if you've got a plane wave that's coming through, those waves are all going to be lined up in a plane or in a line if we look at it 1D and 2D. And you can see every point on this wave is going to be a source of a secondary wavelet. Every single one of them. Those secondary wavelets all propagate spherically from every single one of those points. So I can draw a series of concentric spheres or circles around every single one of the points I've drawn. I've probably drawn too many of them. Let me try it again with only a few of them so you can see better what's going on. Sometime later, the new position of the wave is the line that's tangent to all of those expanding wavefronts. In this case, where is that tangent line? I haven't drawn all of them, but there are an infinite number of them because there's an infinite number of points I can draw, and all of them will define a tangent point that is parallel to the original wave. This is how plane waves propagate according to Huygens principle. It is, in fact, that every single one of those points is expanding spherically, but they all line up so that each of these individually emitted secondary wavelets line up to give you another plane wave over here. And then the process just continues. Each one of those points will emit a secondary wavelet that will give you another one, and the whole thing propagates in a straight line. The tangent to all those waves is still a straight line. This works for a spherical wave too. So the plane wave. What if you have a spherical wave to start with? You can play the same game. This point and this point and this point will all be emitting their own circular. And the line of points that's tangent to all of those secondary wavelets, guess what, is an expanded circle. So this works pretty well to explain plane waves. It works pretty well to explain expanding spherical waves. It works pretty well to explain waves that are expanding in any shape or direction you are interested in thinking about. It explains how if you have some weird square wave or triangle wave to start with and as a source, how that's going to look like a circle when you get really far away from it. Everything turns into a sphere eventually, if it's not perfectly plane. And this is a spherical wave. Okay, this doesn't really explain why, but it does explain, it is a principle for understanding how waves propagate. And that's all we're really interested in now. So going back to our double slit, again, if you were to take all of these points and get rid of all of them except for this one, well, that now is a wave that's propagating out spherically. It's not any different than what the plane wave was doing before. It just doesn't have all of the secondary wavelets next to it to give it a tangent plane that's still a tangent line that's still a straight line. Okay, so Huygens principles tells us this is what should happen when you have two slits. You should get a spherical wave propagating from radially from the center of each one of them. Okay, let's go back to our slits. So we've got these two slits. We've got a plane wave incident upon them. And now you've got, again, spherical waves coming out from both sides. If you were to put a screen over here at some distance away, you might want to know what will those waves interfere and how. So let's say we've got some point up here on the screen. You've got some distance that's going to be covered from slit 1 to that point, and you've got some distance going to be covered from slit 2 to that point. The question is, will those waves interfere? And if so, how? And that's the double slit interference pattern. And that's why, so it's really just a geometry problem at this point. figuring out how those waves are interfering. You're shaking your head, Bailey. You hate this problem. Okay. Well, we're going to spend the next week on it, and either you're going to hate it even more, or you're going to learn to love it. And maybe it'll be the second of those. Keep an open mind, though. You never know. It might be amazing. It really is, to start, just geometry. And really, to finish, it's all just geometry. We just have to figure out what it is. So let's see if we can. I assume you've seen this at some level before. Did you derive? I assume you derived the equation for where the maxima are. We're going to do it again. It's going to take us about 5 minutes. And then we're going to do some more interesting stuff. So bear with me. I know even if you've seen this before, that's okay. So let's do, this is all pure geometry. Oh, I've got some things in PowerPoint. Oh, there's Huygens principle, drawn better than I could have, and a diagram from the book, same sort of thing. This is the diagram that I'm going to try to represent on the board right now. So I'm going to come back to this because it's going to be much clearer probably than the scribbles that I'm going to be writing, but I think it's helpful to also write it down with me one at a time and not just look at the whole thing at once. So let's actually draw the triangles. So let's define our two slits. We've got one of them here and one of them here. Let's define, so this is the plane of some wall right there. Let's define our screen over here somewhere. Let's define another point over here that's going to be the point that we're interested in determining whether we've got interference that's constructive or destructive. And then all we have to do is figure out, draw some lines. There's a line, and there's a line. So we can define some things. For instance, let's set the distance between these two slits to be d. Let's define the distance between the center of these two slits and the screen to be capital L. Now, we've got two different path lengths. One that the light takes from slit 1 and one the light takes from slit 2. So let's call this R1 and let's call this R2, those two different path lengths. It's helpful to have some angle here. I'm going to draw, now the angles are a little bit different between the two slits because they're slightly different slits. We are going to almost always have situations where L is much bigger than D, so that angle is not terribly different between the two slits. And we're going to make the assumption that we can just define a single angle, maybe defined to be the angle that's defined from the center of those two slits to straight towards the screen to the point on the screen that we're interested in talking about. Okay, we'll call that theta. Now, this is going to be a little bit strange because that same angle for R1 and R2 is going to be a little bit different, but we're going to make the assumption that that those angular differences are small enough that we don't have to worry about it. If you really want to do this right, or if you've really got a large slit separation compared to your screen, you have to worry about those angles. We're, for light, almost always talking about slits that are extremely close together and usually macroscopic slit distances. So we never really have to worry about the distances in those angles. So we're not going to. It makes our life a lot easier. Okay, so let's draw. So what is R1 and R2 are not the same. What is the difference in length between R1 and R2? In fact, we can draw some interesting lines here. For instance, this is a perpendicular dropped from one of the slits to the length of the arm extending from the other one. Okay, so we know that this little thing here, I'm going to call delta L, is how much further the light from slit 2 has to go compared to the light from slit 1. So I'm going to say R1 or R2 equals R1 plus delta L. Okay, so I've made this an isosceles triangle here, and I've got a little bit of extra leg on one of them because of the way the geometry is set up. Make sense? So all we care about really is what delta L is. We don't care what R1 and R2 is. We care what delta L is. Because just like the homework problem where you were lining up how those waves were offset, all we care about is whether we're constructively or destructively interfering those two waves. If delta L is an integer number of wavelengths, what's going to happen? You'll get constructive interference. They will be perfectly in phase. If it's a one phase off, if it's two waves off, if it's three waves off, doesn't matter. You come back to being perfectly on phase again. And though you will get constructive interference. If it's exactly a half a wave off, you're going to get destructive interference. It doesn't matter if it's a half or 1.5 or 2.5 or 3.5. You're going to get a minimum, and the peak of one will be the trough of the other, and they will add to zero, and you will get zero intensity. It will be completely destructively interfering with itself. That's all that matters. Delta L. If delta L is an integer number of wavelengths, then waves line up and you get constructive interference. If delta L is half integer, then exactly the opposite happens. Waves are 180 degrees out of phase. And that means destructive interference. The intensity equals 0. Okay, so this sets up our geometric situation pretty easily. We've got a triangle here. This is the triangle of importance right here. I'm going to draw it in red. That's our triangle that's important. It's a right triangle. We know that's a right angle. What is this angle right here? It is just theta. So, and what do we want to know? We want to know, and so we know what D is. That's usually a given. We know what theta is. That's usually a given. We can use those two things to figure out what delta L is. Okay. So, this is theta. We want to know. We have the hypotenuse and we have opposite. What function is that? Sine theta is opposite over hypotenuse. So sine theta, opposite is delta L, hypotenuse is D. Good so far? Excellent. We can solve this for delta L. Delta L equals D sine theta. So for constructive interference, delta L is an integer number of wavelengths. So it is equal to, let's say, m times lambda, where m equals 0, 1, 2, 3, etc., 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 etc. Any integer. So put those two together, plug that in for delta L, and you get probably an equation that you may remember from last time. For maxima, the peak of the intensity distribution, where you get the most constructive interference you possibly can, m lambda equals d sine theta. Sorry? M is any integer, 0, 1, 2, 3. Lambda is the wavelength of the light, or any wave. This is doesn't have to be light waves. This can be any wave. And sine theta is the angle which you're talking about with respect to the center point, as seen from the slit. Where are the minima? It's a very similar formula. The only thing that changes is instead of having integers, you have half integers. Close. That would only give you the actual every other peak, though. It's almost m over 2. It's very close to that. Maybe. And then maybe another way of saying m plus a half. Lambda equals d sine theta. That make sense? And that way you're going to get a half and 1.5 and 2.5 and 3.5 and 4.5 and 5 and all of the half integers. Okay, good. We spent 5 minutes and we derived probably the only equation you needed to do double slit interference things in Analytic 2. So what does this mean? What is it? So let's actually go back so you can see this a little bit better. Here is, again, exactly the same thing I've drawn, but far cleaner and easier to see probably. This is in the book again, or any book, intro physics book, this diagram, some version of the diagram will be there. You can see the triangle we've drawn, much similar to the way we've done before, the path length difference delta L. You can see the entire geometry of what we've done. What is this going to look like on a screen? So if you were to plot, so here's our two slits. Actually, let me give myself a little more room. Draw these two slits. You have a screen over here. What's that going to look like? You're going to get so this is, let's say, intensity going in this direction. So you can sort of see some sort of, you're going to get a maximum at the center where theta equals 0. And it's going to look like this. So there's m equals 0. Here is m equals 1. M equals 2. I should say m can be negative 2, right? This is m equals negative 1. This is m equals negative 2. There's all of the peaks. Here is m equals a half. Here's m equals 1.5. And negative half and negative 1.5 and all of those things as well. Great. So if you had this is again as a function of wavelength or as a function of angle. So if you had a curved screen around your slit, there was a perfect circle, those peaks would be evenly spaced around the circle because these are integer equal wavelengths theta's apart. Theta's linear, right? If you have a flat screen, that's not true because as theta gets larger and larger, the actual physical distance on the screen is going to get larger and larger as you get closer to 90. So if you've got a physical flat screen, they're not going to be equally spaced, but only because you're running out of, only because of how the geometry works. They are equally spaced in angle, but not on a flat, not in physical space on a flat screen. Okay. Okay. Now we're going to do something that you did not do last semester, which is derive the functional formula for that equation that you're seeing there. I don't want to know just where the peaks are. I want to know what intensity as a function of angle is. I want a formula that gives us the intensity on the screen as a function of angle away from the center line. That's our next goal, to derive that formula. And hopefully learn something about math and physics along the way. So we need a new math technique. And this is one of the cool things about this whole project, is we get to learn some new math. So we want to derive the formula. And we get new math. And that new math, and this may be taught in some sort of wavelets class in the math department, but it probably isn't covered in Calc 1 through 3 or differential equations or anything like that, is called phasors. What? P-H-A-S-O-R-S, that's right. Which is not to be confused with phasors with an E, which was the slide that I was going to next with the joke of Star Trek. Phasors, which you can set to stun. Phasors, which always shoot to kill, obviously. Okay, so what is a phasor? Good question. Let's talk about what a phasor is, and then I'll come back to this slide, which will show what a phasor is after I've told you what a phasor is. Okay, so let's take linearly polarized light, regularly polarized light. So you've got some regularly polarized light that's passing by. I shouldn't even say regular. We haven't talked about any other kind of polarization. So it's just polarized light. There are other weird kinds of polarizations, but don't worry about it for this class. It's just straight up polarized. So you've got some point in space, and you've got this light wave passing by. The electric field of that wave is going to be pointing in a particular direction at a given time. Let's say, I don't know, it's there at a given time, right? As the wave passes into the plane, right? It's going to vary over time though, right? So it's going to be from going in that direction to be going in the other direction, and then back, and then back, and then back, and then back. It's going to be oscillating back and forth. So if you look at over time, it's going to be occupying a phase space that looks like that. But it's always going to be knocking back and forth between those two orientations. It's never going to change. That's what polarized light means. It's always pointing in the same direction. Okay. You can represent the phase of that wave it's going by with a phasor. That's what phasors are good at. That's why they're called phasors. This is going to get confusing because there's going to be directions in here that do not correspond to the actual direction of the E field. So I wrote this down so that you can see that there are directions for the E field, but we're not really going to be worried about that ever again. We don't care which direction this wave is polarized in, whether it's this direction or that direction or that direction or that direction. You can write down the same phasor for each one of those. We're really only interested in, are we at a peak of the wave? Are we at one of the descending nodes? Are we at the trough of the wave? Are we at one of the ascending nodes? Or are we somewhere in between? And we want to know what the amplitude of this wave is. Those are the two things we're interested in for phasor. What phase of the waves we're in, and what the amplitude is. So let's recall the equation that we wrote down for the electric field of an electromagnetic wave. EM, just the magnitude of it. Again, I don't really care what direction it's pointed in. I'm going to take away the vector. This is the magnitude of the electric field as it passes a particular spot. EM times sine of kx minus omega t. That's what we wrote down before. We didn't care about an arbitrary phase angle, but let's go ahead and put an arbitrary phase angle in there now because we're going to be thinking about phases more. The plus theta phi naught, again, doesn't change the amplitude of the wave or the frequency of the wave or the wavelength or the wave speed. It just changes where it physically is at t equals 0. That's all it does. Okay? At t equals 0, x equals 0. So, this phi naught is completely arbitrary. It doesn't make any difference. We can set it to 0, and we will normally set it to 0, except when we're interested in knowing how two waves are different in phase. And then it's going to be important to have that there because we need to, that's going to be an important part of the whole thing. Okay. So let's define, this is a lot to write out. I don't want to write it out every time. Let's define phi to be everything inside the sign. So in other words, it's kx minus omega t plus phi naught. Now, of the two things in here, kx and phi naught are both constant in time. They're not changing. Once you've defined it for the wave, those two things remain constant. Omega t is changing as t propagates. The omega t term is, as t goes along, but those two terms are not. The only thing that's changing with time is the omega t term. So we can write this as negative omega t plus kx plus phi naught. And let's define this to just be a number phi 1. So it's not changing ever. We're not really worried about it. We can just parameterize it as something. Let's say it's phi 1. So we can talk about this phi then is just minus omega t plus this phi 1 term. You can kind of think of this now as a vector. How is it a vector? So let's talk about, we're going to define some axes that have no physical, are not a physical axis representation. Let's call it U and V. And the phasor is defined to be this. It has length equal to the amplitude of the wave. In this case, EM. And it has an angle that is the entirety of the things inside the sign. So how is this going to happen over time? Well, we've got a phi that has a constant term and a minus omega t term. So as time progresses, so let's say you've got at some time t, you've got a phasor that looks like that. It's got length em and it's got angle phi. What's going to happen to that as the wave goes by and time progresses? What's going to happen to that phasor? Is EM going to change? No. The angle will. What's going to happen to this thing? It's just going to loop. It's just going to loop around with time. As time gets bigger, the angle gets bigger. There's a negative sign on there. Normally, you'd think of it going this way. It's actually going to go the other way because the negative sign doesn't really matter, though. It's just going to loop around. That's what phasors do as waves go by. They just make loops. It's a little weird. And it's not clear at all why this is useful yet, but we'll get there. This is what it looks like. This is what it looks like. So this is the phasor. And you can think of, why is it useful? Well, we know that EM is the amplitude. The projection of this phasor onto the V-axis or the U-axis, I can't remember which is which now, doesn't matter, onto one of the axes is the actual magnitude of the electric field at that time t. And so as this wave goes by, let me play this. This is the actual value of the field. It's the projection of this onto one of these axes. And you can see it gives you a nice sine wave. All that's happening with the phasor, it's mapping out this circle. But the projection of that circle onto one of those axes gives you the amplitude of the wave at that instant in time. And as you let it go, it maps out the amplitude of the wave at all times, moving up and down. How does this help us? Let me write down some of those things I just said. The magnitude of the E field at a given time, at time t, is the projection of the phasor onto the v-axis. This doesn't give you the direction of that the E field is pointing in. You know nothing about the direction that the E field is pointing in. You don't really care though for this point. This is an exercise in figuring out what the amplitude of the wave is and the intensity of the wave. That's all we really care about here. So how does this help us? How do phasors help us? Imagine that you have two linearly polarized sources of light incident upon the same point. That's where things get useful. And this is where the geometry helps us. The phasor of the sum of two waves that are coherent and polarized and interfering with one another and satisfy all those conditions is equal to the superposition of the two independent phasors. You add them, you can add phasors like vectors, head to tail. If you have two waves incident upon one another and you have two different phasors for them, you can add their phasors and the resulting phasor will be the phasor of the resulting added waves. What does that look like? Imagine that you've got two waves that are in phase, right? We did this example. This is a simple example, but what do the phasors of those two waves look like? Well, they've got the same amplitude, so they've got the same length, and they've got the same, they're aligned. When one's pointing to the right, the other's pointing to the right. When one's maximum, one's a maximum. So here is phasor 1, and here is phasor 2. They're together. And since the frequencies and the wavelengths are the same, as one rotates around, the other is always also rotating around at the same rate. You add those two together, and you get a wave that's twice as long, rotating in the same way, with the same frequency. And that's exactly what you get, a wave that has twice the amplitude and the same period in wavelength and frequency. What if you have two waves that are completely out of phase? I drew that wrong. It'd be easier to draw two waves out of phase, but it's not as easy as you think. Then the phasor diagram looks like this. Again, phasor 1 is still like there at that point, but phasor 2 is pointing in the opposite direction because it's 180 degrees out of phase. And if you add those two head to tail, what do you get? You get nothing. You get 0 amplitude. And it doesn't matter, these two will always be pointing against each other as they go around, and they'll always add to 0 as it goes around. Okay, so that's not very useful, and it's not anymore, I mean, it's useful, but it's not any more easy to deal with this thing than it is to deal with just adding those two things up. This becomes powerful, though, if you have waves with different amplitudes, or waves with different, that aren't completely in phase or out of phase. You can add very easily now in vector space or in phasor space to waves that aren't perfectly lined up or perfectly anti-lined up. The geometry isn't that hard to figure out. Whereas the sign doing this without phasors becomes a rather difficult exercise. Okay, I'm out of time. Let me just see if I can give you a demonstration for how this works. Here are two non-aligned waves that are adding up. And you can see how the phasor addition works. You've got the two waves in blue and red, and the purple is the resulting wave. And you can see how in fact you do get the sum of these two amplitudes are giving you this, and you can see how these two phasors are moving around in lockstep with one another, and you're getting a new sine curve that has the same frequency and wavelength as before, but with a slightly different phase and a slightly different amplitude. The phasor, though, works really well to tell you what that new amplitude and phase is. Okay, we're going to do a demonstration next Monday, which will be to do an example like this with using phasors and without phasors, and you'll see how much easier the phasor method is. So have a good weekend. Try the kappa. It's going to be fun, and I'll see everybody Monday.